Hello, everybody. Welcome to the colloquium talk of week 11. Our speaker today is Pam Gorkin from Bucknell University, and she's gonna talk about the fantastic topic, Crouzex Conjecture, and of course, relation to finite Blaschke product. Pam, please.
Okay, so this is the Blaschke product section, but I'm going to start by talking about Crouzex conjecture. So the setting is that you have an n by n matrix, and you have a complex polynomial p, and if you can assume the norm of p is at most 1. And we define the numerical range of the matrix to be the inner product of ax with x, where x is a vector in Cn and the length of x is 1. So the numerical range is a subset of the plane, and here are some facts about it. First, the numerical range of A is a compact convex subset containing the eigenvalues of A. Next, it's a unitary invariant. So if you have two matrices that are unitarily equivalent, they have the same numerical range. And for me, that means that I won't always say that this is unitarily equivalent to something. I'll just talk about the numerical range. And another fact that sounds a lot easier to prove than it is the elliptical range theorem that says that the numerical range of a 2x2 matrix is an elliptical disk. And generally in this talk, I'll be focusing on matrices of norm less than 1 so that the numerical range is strictly contained in the open unit disk. So that's the numerical range. And this first theorem sort of in this direction is von Neumann's inequality. And it says that if you have a contraction on a Hilbert space, then the norm of a polynomial of the operator is less than or equal to the sup over the modulus of P of Z for Z in the disk. Now, there are many theorems of this type, many generalizations, many versions of this, but the one that I'd like to focus on is due to Michel Crouzeix. And in 2004, he showed that if you take a 2x2 matrix and you look at a polynomial of that matrix, then it's less than or equal to 2 times the maximum of the modulus of P of Z, where Z is in the numerical range of A. So if you think about this compared to von Neumann's inequality, I'm saying you can look at a smaller set, take the maximum of the polynomial over a smaller set, but you have to put this constant of 2 out in front. And he conjectured that if you had an n by n matrix, then for all polynomials, all n by n matrices, the norm of P of A is at most 2 times the maximum of the modulus of P of Z, Z in the numerical range of A. So it's the maximum now because I told you that the numerical range is compact. So I'm going to be focusing on this conjecture. It's motivated a lot of really interesting mathematics. And here's some evidence for it and an explanation of why the constant 2 shows up. So if we look at a little 2x2 Jordan block with zeros down the diagonal, then it follows from the elliptical range theorem that the numerical range is the closed disk centered at 0 of radius 1/2. And it's easy to see that the norm of the matrix is 1. So if you take your polynomial P to be Z, it's supposed to work for all polynomials. Then what we get is P of J2 is just the norm of J2, so that's 1. And then on this side, the maximum of P of Z over the disk of radius 1/2 is 1/2, and therefore you must have 2 here. So since this is supposed to hold over all polynomials and all matrices, you need at least 2. Okay, so one thing you may think about is, well, I'll just find the boundary of the numerical range and I'll plug it into my function and I'll see if that works. It's very, very hard to find the boundary of the numerical range in general, But for Jordan blocks, it's not so hard. So if you take a Jordan block with zeros on the diagonal, the numerical range is the closed disk of radius cosine pi over n plus 1. And so again, you see when n is 2, the numerical range is the closed disk of radius cosine pi over 3, and that's the half that I mentioned earlier. A proof of this appears in a 1992 paper of Hagerup and Delaharp, in which they looked at nilpotent matrices. So they looked at contractions for which t to the n is equal to 0 for n greater than or equal to 2. And they showed that the numerical radius, so I'm denoting that by w of t, so that's the farthest the numerical range is from the origin, is at most cosine of pi over n plus 1. So in some sense, you can think of these Jordan blocks as being really big, having big numerical range. Okay, so there's the Crouzex conjecture again, and now I'm going to go through some early evidence. So we've already talked about the 2x2 case. It holds there for all 2x2 matrices. And if we go back to the elliptical range theorem, that tells us that the numerical range is an elliptical disk. So a simpler question would be to ask, is the conjecture true when the numerical range is elliptical? And I'll talk a little bit about that. But I want to say that it's not easy to tell when a numerical range is elliptical. So there are some papers of Spikovsky with some other co-authors in which this is addressed for relatively small matrices. At the time Crouzeix wrote this paper, Badea noticed that the conjecture is true when the numerical range of A is a disk. And then in 2007, Crouzeix showed that if you take any matrix and any polynomial, you can put a constant of 11.08 out in front and the conjecture would hold. So with that constant. He notes in that paper that the proof proposed here for the inequality is still intricate and only uses old-fashioned mathematics, but I've found no help in the modern literature on operator theory for this specific question. So I'm going to talk a little bit about what these proofs look like. And in 2017, Crouzeix and Palencia gave a very clever proof. This is probably the easiest of the proofs to read that show that you could look at a constant of 1 plus the square root of 2. So the norm of P of A is less than or equal to 1 plus the square root of 2 times the sup over the numerical range of A. Okay, this is the, it's very clever, the proof, and it's very beautiful, but it has a key lemma in it. And if you take that lemma, if you focus in on that, you can actually simplify that the proof of the key lemma as well. And this is due to Ransford and Schwenningen. So we look at A of omega, and that's the set of functions that are continuous on the closure of omega and holomorphic on omega. And the norm of F restricted to omega is just the supremum norm. So the lemma that they isolated is an operator theoretic looking lemma that says let T be an operator on a Hilbert space and omega a bounded open set containing the spectrum of T. If for every F in that space, A of omega, there exists a G in A of omega, such that the norm of G is less than or equal to the norm of F, and the norm of F plus G, F of T plus G of T adjoint is less than or equal to 2 times the norm of F of omega, then the norm of F of T is less than or equal to 1 plus the square root of 2 times the norm of F of omega. So this is a key lemma that they prove for particular functions. And the proof in Ransford and Schwenningen is really functional analysis. It's very short, but here's where it sits in this collection of things. In the proof in Crouzeix and Palencia's paper, the G in this is the Cauchy transform of F. So that's antilinear and unital. Ransford and Schwenningen show that this is sharp, the inequality is sharp via an example, but their example is actually antilinear and not unital. And so they propose another version of this, which if you can solve it, would solve the Crouzex conjecture. And that's a uniform algebra view of it. I won't be focusing on that any more than to say that that's out there. But some other evidence for the Crouzex conjecture is due to Greenbaum and Overton, where they looked at the ratio of the norm of P of A over the numerical range of A divided by the norm of P of A. And they used Chebfun and found that this supports Crouzex conjecture. Some more evidence. Greenbaum and Choi looked at matrices of this form. So if A were 0 and all the lambdas were 0, this would just be the Jordan block. This is what they call a perturbed Jordan block. But as far as the numerical range goes, you can just assume the lambdas are 0. And so when I talk about this, I'll be assuming the lambdas are 0. If you get the Crouzex conjecture in that situation, you also get it in general, with general lambda. The same techniques can be adjusted, and in 2013, Choi showed how they could be used to prove it for this weighted shift. And in 2017, Gleider, Kurula, and Lindstrom looked at 3x3 matrices with elliptical numerical range and one eigenvalue at the center of the ellipse. These three results have the same basic structure to their proof, which I'd like to show to you. So these are the matrices that Gleider, Kurula, and Lindstrom looked at. Their proof is quite technical. So here's the idea in all of those three. Suppose we could find a bijective holomorphic map from the interior of the numerical range to the disk. And you'll be able to extend it to the closures, so to the numerical range, to the closed unit disk. In these cases, they're able to compute G of A, and they show that it's similar to a contraction where the norm of C is less than or equal to 1. And they get that the norm of X times the norm of X inverse is at most 2. So if you put that in, you get the norm of P of A. Well, that's the norm of P composed with G inverse G of A. But G of A is XC, X inverse of A. And if you think about how polynomials work, you can pull the X's out. Okay, so if we now crash through with norms, we have this. And since C is a contraction, we can apply von Neumann's inequality here. So the norm of X times X inverse will be replaced by 2. We get 2 times the norm of P composed with G inverse of D, but G inverse of D is going to give you the whole numerical range. So that's 2 times the maximum of the modulus of P of Z for Z in the numerical range of A. And that is the basic structure of those proofs. Of course, you have to find G, and you have to be able to compute the norm of X. But let's look at this perturbed matrix, and it'll show you how it fits into this body of talks that people have been giving. So assuming lambda is 0, if A is 0, we just get the Jordan blocks, so we can assume A is between 0 and 1. If A is bigger than 1, the numerical range is very big. So in this setting, this is a contraction. All eigenvalues are in the open unit disk, and the defect index, or the rank of I minus the matrix, adjoint of the matrix times the matrix, is equal to the rank of I minus JA star, which is 1. And so Greenbaum and Choi were looking at examples of compressions of the shift or model space operators. So that takes us to something that you've seen for a whole week. So let me just run through some of the basics. So here, H2 is the Hardy space. That's the set of functions with power series with square summable coefficients. An inner function is a bounded analytic function on D with radial limits of modulus 1 almost everywhere. The shift operator goes from H2 to H2. So you take a function in H2 and multiply by Z. And the adjoint of the shift operator, you take f of Z, subtract 0, and divide by Z. And it's known that the non-trivial invariant subspaces under S are of the form UH2, where U is a non-constant inner function. That's Berling's theorem. So we know the invariant subspaces under the shift, and therefore the invariant subspaces of the adjoint, that's the model space operator model space KU, which is the orthogonal complement of UH2 in H2. So in the setting that I'm looking at, we will be looking at the orthogonal complement of a finite Blaschke product times H2. So these will all be finite dimensional. The operators that we look at are compressions of the shift. So they go from the model space to the model space. And I remind you of what the definition is down here. You take your function f in the model space, multiply by z. Now maybe you're out of the model space, so you project back down. Theta is a finite Blaschke product in this setting, and the perturbed Jordan block that I just talked about with zeros down the diagonal and a between 0 and 1 is the compression of this shift S theta, where theta of z is z to the n minus a over 1 minus a bar z to the n. When a is 0, the usual Jordan block is the compression of the shift where theta is just z to the n. Okay. So why would this help us? Well, first, we know a lot about the numerical range of compressions of the shift. The theorem I want to focus on is due to Gao and Wu, and it says that if you have an operator that is a compression of the shift or unitarily equivalent to it, and at any point on the unit circle, you can find an n+1 gon that is inscribed in the unit circle, and that circumscribes the boundary of the numerical range of T, and lambda is one of its vertices. So all the vertices of your polygons are on the unit circle, and it circumscribes the numerical range. Now, it's really nice to picture this theorem, so I have to take a step back and tell you how to picture it. So to picture these things, we first have to picture Blaschke products. On the left is a degree 2 Blaschke product. On the right is the plane. And I've just colored the plane according to the rainbow: red, orange, yellow, green, blue, indigo, violet. And you think of the function as the domain over here. When you plug into the function, this is a window of size from -2 to -2, -2 to 2 and -2 to 2. So the unit circle is in here. And you see there are 2 zeros. The way you get the colors is you go to the point and you ask where B maps that point. So if B maps that point to 1, then you're going to color it red. And if it maps it to -1, you're going to color it light blue. And you do that at every point, and that allows you to see the argument of the Blaschke product at every point. I also have included the contour lines here. There's a lot more you can do. This is done with MATLAB and a package called CFE GUI. So this is how you can picture the Blaschke product, and that means that here on the unit circle, The Blaschke product takes the value 1, and then over here, it takes it again. So I can see that it takes the value 1 when it's colored red. And we know that to get the numerical range of S theta, what you do is you take a point on the unit circle, and then you're going to take a circumscribing polygon. And the vertices of that circumscribing polygon you get by looking at where z theta of z is equal to lambda. So you're looking at all the points that z times theta of z gives the same color to on the unit circle. And you can actually then find the points on the boundary of the numerical range using a formula that's kind of messy to get the points of tangency. So that means what I'm looking at in this picture is one of the polygons where z theta of z maps all the vertices to the point 1. And so if we go back to the Galois-Wu theorem, it's saying do that for every color. And then what you see is the numerical range. So that red curve is the boundary of the numerical range. So that's an extremely useful theorem. But we also know a lot about Blaschke products. So if we focus in on finite Blaschke products, it becomes clear that the best way to think of them is in the hyperbolic setting. So if we compare polynomials and Blaschke products, polynomials have n solutions in the complex plane. Blaschke products have n solutions in the open unit disk. Polynomials are self-maps of the Riemann sphere of valency n. Blaschke products are self-maps of the disk of valency n. Polynomials are products of the conformal self-maps of C times a constant. Blaschke products are products of conformal self-maps of D times a constant of modulus 1. Polynomials are determined by their n-1 critical points in C up to composition with a self-map. Blaschke products are determined by their n-1 critical points in D up to composition with a self-map. So this suggests thinking about Blaschke products hyperbolically. And basically what that means is when we think about when things are big, we think about when Euclidean disks are big. Instead, we should probably be thinking about when pseudo-hyperbolic disks are big. So what I'm suggesting is replacing the modulus of z minus c less than r by the modulus of z minus a over 1 minus a bar z less than r. So one's a Euclidean way of thinking of things and one's a pseudo-hyperbolic way. But this isn't really a change at all. Probably you know that a pseudo-hyperbolic disk is a Euclidean disk, but every Euclidean disk is also a pseudo-hyperbolic disk. So I'm not really saying anything new, I'm just changing the point of view here. So I'm thinking about this now in a different setting. And that enables me to restate the Crouzeix conjecture, but a simpler form of it. So if we go back to Sarason's work in 1967, he showed that if you have an H infinity function and you look at f of s theta, then that is the same as restricting your function to k theta, multiplying by the function f, and then projecting down. And using that theorem, you can show that if the B is a finite Blaschke product and the degree of B is less than theta, then the norm of B of S theta is 1. So let's now go back to the Crouzex conjecture, but assume that this is happening, that the degree of B is strictly less than the degree of theta. Then the Crouzex conjecture in that setting says that the norm of B of S theta is 1. We're asking that the maximum of the modulus of B of Z over Z in the numerical range of S theta is bigger than or equal to a half. So we're just asking that this maximum be bigger than or equal to a half. This is now just a complex analysis question. So the complex analysis question is, I give you two finite Blaschke products. The degree of one is less than the degree of another. Is the maximum of the modulus of B of Z bigger than or equal to half over the numerical range of S of theta? Now, when you think of all the cases where Crouzex conjecture has been proven true, and we're talking about numerical ranges of S theta, we know this is true. Okay, I'm calling this a level set conjecture, or just LSC. And the reason I'm calling it that is if we look at omega BR, so that's what I'm going to call the open level set of B. The components of these are what are sometimes called tracks. And we assume that the degree of B is less than the degree of theta. Then we're just saying the numerical range of S theta cannot be contained in the 1/2 level set of B, open level set. Okay, so when you view it like this, you sort of hope that there's lots of other information that you can use. So early on, Valeron and Mary Cartwright looked at level sets. And then in the 80s, Berman, Stevenson, and Sundberg also looked at level sets. Berman showed that if you have two inner functions, and if here I'm talking about the boundary, so the equality level set is where it's equal to R is equal to L of theta 2S. So they share the same level set, but different levels, then theta 1 is actually lambda times theta 2 to the alpha. At about the same time, Stevenson and Sundberg showed that if you had two inner functions and they have, now you're looking at the same level set and they have a subarc in common, then theta 1 is lambda times theta 2 for some lambda in the circle. So these are, in some sense, stronger conditions than what I'm requiring. I'm just looking at containment in a level set, but they have much more general functions. So they have inner functions, and I just have finite Blaschke products. So one of the things that's true is that if you have finite Blaschke products with the degree of C less than or equal to the degree of B, and if the open level set of B is contained in the open level set of C, then B is lambda times C. So B, the degree of B is bigger than the degree of C, and that means B should be smaller more often. So you would expect this open level set to be bigger. And what I'm saying is if it isn't, then B is actually a constant times C. So there's a theorem of Gao and Wu that says if you have two compressions of the shift with theta 1 and theta 2 Blaschke, and the degree of theta 2 is bigger than or equal to the degree of theta 1, then the two operators are unitarily equivalent if and only if the numerical range of S theta 1 contains the numerical range of S theta 2. This is the same kind of theorem. So if theta 2 has higher degree, its numerical range tends to be bigger. And so what you're saying is if the littler, the one you expect to be smaller, contains the bigger one, then the two operators are unitarily equivalent. When they're unitarily equivalent, the two finite Blaschke products will have exactly the same zeros. So one will be lambda times the other. So these two results sound very, very similar. Okay, I want to show you how this can be used in a couple of settings. So the perturbed Jordan block is the one that Greenbaum and Choi did. I'm only going to talk about it for n greater than or equal to 6. And I just need to tell you two facts, one of which I told you before. The numerical range of S with symbol z to the n is the same as the numerical range of the Jordan block. That's the closed disk of radius cosine pi over n plus 1. And then the other thing you need to know is that if you take the cosine of pi over n plus 1 and you raise it to the n, as long as n is bigger than or equal to 6, that's bigger than a half. So I'm going to first prove the result for z to the n. So for z to the n, the numerical range of S z to the n is the numerical range of the Jordan block. That's the closed unit disk. And this Jordan block, if you cross off this row and this column, you just get the n by n Jordan block. So its numerical range is contained in the numerical range of the bigger one that I'm looking at. But z to the n is the cosine of pi over n plus 1 to the n on the boundary. And so it's bigger than a half on the boundary, which is contained in the numerical range. So for z to the n, the result has to be true. What if you take an arbitrary Blaschke product of degree at most n? Can it be less than a half on the numerical range of this operator, the perturbed Jordan block? Well, if it is, then it's less than a half on the numerical range of Jn, but the set where z to the n is less than a half is contained in this disk. That's the numerical range of the usual Jordan block, and that's contained in the level set of C. So the only way that can happen is if C is lambda z to the n, where we know the result holds. Another application is if you can find big enough pseudo-hyperbolic disks inside your numerical range. So let B be a finite Blaschke product with degree less than or equal to m. Then if you take a pseudo-hyperbolic disk of large enough radius, then B will be bigger than or equal to r on that disk. And to see why this is true, if you start with C, on the boundary of this disk, the modulus of C is r, so it's certainly true for C. The degree of B is less than or equal to the degree of C, but this is the R level set of C. And so what you have is the R level set of C is contained in the R level set of B, and therefore B is lambda times C. So again, the result holds. Okay, so here are some cases that we know. For Greenbaum and Choi, we know it for the perturbed shift. Together with Kelly Bickel, we looked at theta of z, which is just a unicritical Blaschke product, z minus a over 1 minus a bar z to the n. We show that the level set conjecture holds for n equal 3, 4, and probably 5, and I'll explain the probably later. Now, there's two ways of thinking about this. You can fix your matrix and change all your polynomials, or thinking about what you get from polynomials, it's enough to look at Blaschke products, so you can do that. Or you can fix a polynomial or Blaschke product and change your matrices. So the third result is if you fix a Blaschke product of degree 2, you can show that whenever theta has degree bigger than or equal to 6, this level set conjecture holds. The proof of 3 is a geometric proof. What I'd like to talk about now are some of the techniques that are used in 2. Okay, so what we know about these unicritical Blaschke products, first of all, you can assume that that A is real. So you can assume it's real and positive. And so I'm going to call it T now, where T is between 0 and 1. And in 2012, Gaia characterized the numerical radii of these matrices. And it's quite complicated to do so. The matrix for A matrix representation for these matrices is of the form Ti plus 1 minus T squared AT, where AT is this matrix that I'm showing you here. Because the T's are constant down the diagonal, you can always ignore them and replace them by 0 as far as Crouzex conjecture goes. And so we begin by looking at that, and then we can transfer everything back to MT. This matrix AT is nilpotent, and that's one of the things Crouzeix studied. When he studied nilpotent matrices, he looked at 3 by 3 nilpotent matrices. And he got an equation for the boundary of the numerical range. So one of the points that I mentioned earlier is that it's very hard to get an equation for the boundary of the numerical range. And I think this makes that point. So here you define MT of S to be this object. The parameterization is actually X hat of S, X hat sub T of S, and Y hat sub T of S. So these are very complicated, difficult to work with, but sometimes it's possible to get a simpler looking curve inside that almost approximates the boundary of the numerical range. And so using some ideas from Crouzeix, we got this characterization that I'm sure doesn't look any better than what I just said, but in low degree cases, you can reduce it down to get a curve that's actually inside the numerical range of this matrix AT. So here's what it looks like in its better form. For n equal 3, the curve is just 1 over the square root of 2 e to the is minus t over 4 e to the I2s. And if you look through all of these, you can start to see a pattern. This is e to the is, e to the I2s, e to the I3s, and then e to the is, e to the I2s, e to the I3s, e to the I4s. This is cosine of pi over 4. This is cosine pi over 5, and this is cosine pi over 6. So perhaps it's possible to find a formula in more generality. But finding these formulas enables us to do some other things. So here's a picture of the curves. The blue is the numerical range because it has to be convex. And this sort of orange is the, excuse me, the inner curve. And you can see that they approximate it really quite well. Once the numerical range is very big, we expect the result to hold. So you really need it to approximate well here. Okay, this is the result I mentioned earlier. I'm calling it a PhD bound. PhD refers to pseudo-hyperbolic disk, nothing else. So this is the result that I mentioned before. And the point is that using these curves, we're able to show that the numerical range of S theta always contains a pseudo-hyperbolic disk when theta is unicritical. So remember that means that theta is just one factor to a power. So when n is greater than or equal to 3, the numerical range of S theta always contains a pseudo-hyperbolic disk of radius 1 over the square root of 2. And when n is greater than or equal to 4, the numerical range always contains a pseudo-hyperbolic disk of radius 1 over 2 to the 1/3. So if you think about what this means together with the result above, the level set conjecture, if where n is greater than or equal to 3, the level set conjecture only looks at Blaschke products of degree 2. And so since this contains a pseudo-hyperbolic disk of rate with R1/2 and M2, the Blaschke product will be bigger than or equal to 1/2. Here, n is greater than or equal to 4. The worst case scenario is when the Blaschke product has degree 3. Degree 2 Blaschke product would be bigger. And we show that the numerical range contains a pseudo-hyperbolic disk of radius bigger than 1 over 2 to the 1/3. Since B would have degree 3, we'd get the result from this lemma. So the level set conjecture holds for n equal 3 and 4. Okay, you can also use this to, and the proof that I showed you using the conformal mapping of the numerical range, to get a bound on P of S theta for all polynomials P. It's the square root of 13 plus the square root of 41 over 2. That's for degree 3. And that value is 2.2. But remember that Crouzeix proved it for degree 3. So the actual result is 2. For n equal 4 and 5, we can get results using Mathematica. But when we use the norm of xt and the norm of xt inverse, this is for n equal 5, we get 2.51 rather than 2. And for n equal 4, it's 2.3, but for certain ranges, it is 2. So this adds additional evidence for the Crouzex conjecture. It's reasonable to conjecture that W of S theta always contains a pseudo-hyperbolic disk of radius 1 over 2 to the 1 over n minus 1, but that's not true, and you can show it with a relatively simple example. Still, it would be interesting to know if it's true in the situation that I've described here for unicritical Blaschke products, whether or not the numerical range of S theta always contains a pseudo-hyperbolic disk of large enough radius. Okay, that's almost the end of my talk. I want to mention that our 2022 calendar is out. This is a complex beauties calendar. And I wanted to point out that February is honoring Peter Duran and harmonic polynomials. Thank you very much.
Thanks a lot, Pam. Let's thank the speaker first. It's kind of the talk that if you continue up to midnight, we sit and listen. It's wonderful. Thanks a lot, Pam. Any question or comments for Pam?
Hi, Pam. I have a question.
Okay.
So we know that, for example, for degree 4 Blaschke products, if they're a composition of a degree 2 and a degree 2, then the numerical range of S theta is an ellipse. So one could ask the question, for those S theta, do we know is Crouzex conjecture true? Do you know the answer to that question?
I do not know the answer to that question, and I don't think that is known.
Okay.
Nathan, there's a recent paper of Simonek, Hunziker, and a bunch of other people in which they look at degree 6 also. Okay. Elliptical ranges for degree 6.
Thanks.
Any further comment or question?
Yes, I have one. Hi, Pam. It's Tom Ransford.
Hello.
So you've done quite a lot of calculations with small matrices. And you mentioned that Crouzeix, right at the beginning, proved the conjecture for 2 by 2. His proof is not that easy. It uses the explicit form of a conformal mapping from an ellipse onto a disk. Right. Do your calculations give any new insights or simpler proofs for the 2 by 2 case?
So not that I know of. So the proof that I described here is not computationally more attractive than Crouzeix, but the geometric proofs are really, they have quite a bit of potential. The problem is that we use something called Fuss's formula. If you know it, it's for when a circle or ellipse is inscribed in a quadrilateral. And those become complicated for higher degree, but there are formulas for higher degree. So I don't know if that would work.
Okay, thanks.
Pam, following what Tom said, Is there a way, or is there a hope to better understand the first paper of Crouzeix? I mean, the one with constant 11.08. I mean, of course, it's replaced by 1 plus root square of 2, but with different method.
Yeah.
The first one, frankly, I do not understand when I mean, I've read it several times.
Yeah, so the methods that we use here are based on his paper, 3x3 nilpotent matrices. Some of those techniques are the same. So Kelly and I really didn't think about simplifying that. So that's a good suggestion. One thing I think would be interesting to prove, you know how in Sendov's conjecture, it's known that Sendov's conjecture holds when the degree is very high.
Mhm.
Terry Tao did that recently.
Recently, yeah.
I think you should be able to prove that Crouzex conjecture is true when the matrix is very big.
Okay.
So I don't know how big it has to be, but just very big.
Thank you. Thank you, Pam. And there is a request by Siskakis, our friend. Is it possible to share the slides of this talk?
Sure.
Can
Can I just send them to you and then you upload them, or?
Either to me, or it's, if you share it on the chat now, everybody who is present can download it immediately.
Okay, but I have to upload it, right?
Yes,
Or no?
on the chat.
Okay, so I have to go out of here. And okay, I can do that. Okay. Just okay. Sorry.
No, it's okay.
Okay. Okay. That should be it.
Yes, it's there. Thank you.
Pam, I have a question. This is Alex.
Okay.
So maybe I'm missing something, but is there any reason not to consider the conjecture more generally for Hilbert space operators rather than
No.
just n by n matrices?
No, you can do that. Yeah, that's correct. It's just the techniques we use are for finite dimensional operators.
So did the known bounds work in that situation? Do they generalize?
Mm-hmm.
Any further comments or questions for Pam? If not, let's thank her again for this wonderful talk.